You know from personal experience that some solids will dissolve easily in water, like salt and sugar. You also know that some solids won't, like fats and waxes. The same is true of liquids. Water and alcohol are miscible, but water and oil won't combine. Your personal experience tells you what to expect with materials you're familiar with, but it doesn't allow you to understand the reasons why that behavior is occurring. It also won't allow you to make predictions about materials you haven't encountered before. Why do some things dissolve, but not others? What makes water such a great solvent? How does soap actually work? The answers to all of these questions can be understood with a few simple concepts about intermolecular forces. Intermolecular forces. Inter from the Latin, which means between or among. Molecular forces from the Latin, it means molecular forces. We saw before that we can classify intermolecular forces into three categories: ion-ion interactions, dipole-dipole interactions, which includes hydrogen bonding as an especially strong version, and dispersion forces. Remember, these interactions are the result of forces between the molecules, not the chemical bonds within the molecules. Disrupting or allowing to form these intermolecular forces can only result in physical changes, not chemical reactions. These interactions are electrostatic. They involve opposite charges on different particles that are attracted to each other. Those charges might be permanent or transient, they might be full unit charges, or they might be only partial. Regardless of their nature, the attractive forces are always due to a positive charge on one particle attracted to a negative charge on another particle that brings them and holds them together. The larger and more permanent those charges are, the stronger the attractive force will be. If the strength of the attractive forces is determined by the nature of the charges, which of the following intermolecular forces should be the strongest, assuming molecules of about the same size? Ion-ion interactions, dipole-dipole interactions, dispersion forces. Not quite. Dipole-dipole interactions are due to polar bonds within a molecule, but they only give rise to partial charges. There is going to be a stronger force, one that involves larger charges than that. No. Dispersion forces are due to transient distortions of an electron cloud in a molecule. Those are generally going to give rise to very weak forces unless the molecule is very, very large. Excellent. We're on the same page. The interactions between the full permanent charges found in ions are going to be very strong. The expected relative strength of the intermolecular forces is this. Dispersion forces are due to partial charges arising from temporary distortions of the electron cloud. These will be present in every molecule, but it's not likely to be the most important force unless the molecule is nonpolar or very, very large. Dipole interactions are due to the partial charges that arise from non-canceling bond dipoles within a polar molecule. Hydrogen bonds are a special form of dipole interaction where a positively charged hydrogen atom is connected to a highly electronegative atom like nitrogen or oxygen. And finally, ion interactions are due to permanent, full charges between cations and anions. So how do intermolecular forces between the molecules help us understand solubility? We have to think about enthalpy changes. To explain how that works, we're going to need a diagram. Grab your pen. Whether two materials can mix, like a solute dissolving in a solvent, depends on the enthalpy change for that process. We can imagine this occurring by three steps. Step one, separate every solute molecule from every other solute molecule by adding enough enthalpy to overcome the attractive forces among them. That's a positive delta H, absorbing enthalpy. This is an endothermic step. Step two, separate some of the solvent molecules, maybe not as completely as we did with the solute, but enough that there are spaces between some of them. That's also a positive delta H, absorbing enthalpy, another endothermic step. Step three, combine the solute and solvent molecules together. Now that means new attractive forces can form. That's a negative delta H. This releases enthalpy. It's an exothermic step. If the attractive forces between the solute and the solvent are much weaker than those among the solute molecules alone or the solvent molecules alone, the enthalpy released by mixing solute and solvent is far less than the enthalpy absorbed by separating them in the first place. More energy goes in than comes back out. That's an overall highly endothermic process. It's uphill. That solute, it won't dissolve. But if the attractive forces between the solute and the solvent are stronger, or at least comparable to those among the solute molecules and among the solvent molecules, then the enthalpy released by mixing solute and solvent is either greater than the enthalpy absorbed by separating them, in which case the process is exothermic and favorable, or at worst, it's only slightly endothermic. You'll probably be able to dissolve that material by heating it up a little. Only when the solute-solvent interactions are at least comparable to the solute-solute interactions and the solvent-solvent interactions will something dissolve, because only then will the trade-off of intermolecular forces be energetically favorable for both partners. So if you want to understand solubility, you need to think about intermolecular forces. But if you want to understand intermolecular forces, you need to think about molecular structure. Why does sugar dissolve in water while fat doesn't? It has to do with the structure of those molecules. Let's get small. In chemistry, the word sugar can refer to any one of a large number of molecules with similar structures. But in everyday conversation, the word sugar refers to common table sugar. That's a specific substance. Chemists call it sucrose. What does it look like? The structure is pretty complicated. 2 different rings of carbon atoms, but all around those rings are OH groups. In solid sucrose, these OH groups will form hydrogen bonding interactions to neighboring sucrose molecules, just like the OH bonds in water will form hydrogen bonding interactions to surrounding water molecules. But if the sucrose is mixed into water, now the OH groups form hydrogen bonding interactions between the sucrose molecules to the surrounding water molecules instead. Sugar and water both have hydrogen bonding, so when they mix, they can share the same attractive forces with each other. The interactions gained are just as favorable as those that were lost in the individual substances, so the sugar can dissolve. Lard is made up of nonpolar substances. Triglycerides form from molecules like palmitic acid and oleic acid. These molecules do have some polar groups in the center part of the molecule, but they're made up almost entirely of long chains, 16 or 18 carbons long, of nonpolar CH bonds. The intermolecular forces among these molecules are primarily dispersion forces. Water won't separate and give up very strong hydrogen bonding interactions with other water molecules just to make room for weaker interactions to nonpolar CH bonds. These molecules cannot dissolve in water. However, lard will dissolve in a nonpolar solvent, like benzene, because now the solute and the solvent intermolecular forces match. They both have dispersion forces, so they can form comparable interactions with one another. Now let's see if you can apply this idea to another example. Which of the following materials will not dissolve in water? Table salt, or sodium chloride. Oxalic acid. Naphthalene. No. When table salt, sodium chloride, is placed in water, the ions will dissociate quite easily. They lose ion-ion forces between them, but in return, they gain very strong ion dipole forces because each ion will be surrounded by multiple highly polar water molecules. Those intermolecular forces are quite comparable, and salt will dissolve easily. No, oxalic acid is a polar molecule, and it can form hydrogen bonds. It has the same intermolecular forces as water, so it's also going to dissolve. That's right. Naphthalene doesn't have any polar bonds, it doesn't have a dipole moment, and there's no way for it to form hydrogen bonding interactions. Naphthalene only has dispersion forces. The water molecules are not going to trade the hydrogen bonding interactions with other water molecules to make room for the naphthalene. Naphthalene can't dissolve. What about when we combine liquids? Some liquids won't mix together, while others will combine and they'll form homogeneous solutions. 2 liquids that mix in this way are called miscible. The same ideas that can help you understand whether a solid will be soluble can be used to explain whether 2 liquids will be miscible. Let's try some examples. To the lab. In this flask, I have water. In this beaker, some methanol. Methanol is the simplest alcohol. One carbon connected to an OH group, the functional group that makes it an alcohol. Look at the structures of those compounds and think about the intermolecular forces. Using the same ideas that we did before, what will happen if I mix methanol with water? These two liquids will mix. They won't mix. They'll remain as separate layers. They'll mix just a little bit, but not completely. They will explode. No, for the two liquids to remain separate, those substances have to have very different intermolecular forces. Molecular polarities can exhibit a pretty wide range, and so can solubilities of two liquids. Sometimes two liquids will combine to form a perfectly homogeneous solution. Sometimes you'll see partial solubility. A little of one liquid will dissolve in the other, the rest will remain undissolved as a second immiscible layer. But for that to happen, the intermolecular forces have to be pretty different. That's not going to be the case with water and methanol. No, that's sodium. No explosions today. That's right. The OH group in methanol means that, like water, it's a very polar molecule and it can form hydrogen bonds. The two intermolecular forces in those substances are comparable. If I mix them, they should combine perfectly. They should form a miscible, homogeneous solution. Now we're going to try adding hexane to water. Hexane's a very different molecule. It looks like this, a long chain of carbon atoms surrounded by only carbon-hydrogen bonds. What's the most important type of intermolecular force in hexane? Ion forces, dipole forces, hydrogen bonding, or dispersion forces? Ion-ion interactions require a permanent full charge on the particles. Hexane doesn't have any charges. Dipole-dipole interactions require a polar molecule due to an unsymmetric arrangement of polar bonds within that molecule. But the CC and CH bonds in hexane are all nonpolar. Remember, in order for hydrogen bonding to occur between molecules, a hydrogen atom must be bound to a very electronegative atom like nitrogen or oxygen, and there needs to be a lone pair on that electronegative atom. The CH bonds in hexane aren't polar enough to give you that kind of a positive charge on the H. That's right, the hexane molecules are nonpolar, so the only intermolecular force that hexane can exhibit is dispersion forces. Water has hydrogen bonding, a much stronger force. The water isn't going to allow the hexane to dissolve. The water molecules, with their very strong hydrogen bonding interactions, will not separate to form much weaker interactions to the dispersion forces of the hexane molecules. As a result, these two solvents are immiscible, and they form two separate layers. Hexanes isn't something you're likely to have lying around, so let's use a more familiar example. Let's try this again with cooking oil.
I've added a little bit of cooking oil to this water. You can see the oil. It's a distinct layer on top of the water. It's a slightly different color. Oil is made of molecules called hydrocarbons, long chains of carbon atoms that only have nonpolar CH bonds. It's just like the hexane that we used earlier. The nonpolar oil and the polar water won't mix. They're immiscible.
Suppose you get some oil on your hands. You can try to wash it off with water, but your hands will still feel greasy. The oil and grease molecules are nonpolar. They won't dissolve easily in water. You could wash your hands in hexane. The hexane will dissolve the oil, but the hexane will also permeate your skin, and it will cause severe damage to your peripheral and central nervous system. Don't wash your hands in hexane. So what do you do to get oil off your hands? You use soap. How does soap work? Well, that's a big question. Here's a compound you'll find in most soap. It's called sodium stearate. Take a look at it. Do you think that this molecule is polar or nonpolar? Let's get small. In a soap molecule, there's a long hydrocarbon chain. So this part of the molecule exhibits only dispersion forces. At the head of the molecule, that's different. There's an anionic carboxylate group. It has a charge, it's very polar, and it can act as a hydrogen bond acceptor. So, should this molecule dissolve in polar water because of the polar head, or in nonpolar oils because of the nonpolar tail? Well, the answer is actually both. When you wash your hands with soap, the polar ends of the stearate molecules interact strongly with water. The groups that interact with the water are called hydrophilic. That means water-loving. But water won't interact with the nonpolar stearate tails. Those chains are driven away from the water. Nonpolar groups like this are called hydrophobic, which means water-fearing. That's actually dumb. Nonpolar molecules don't fear the water. They form much more favorable interactions with water molecules than they do with themselves. But for water, the interactions to the nonpolar molecules, they would be far less favorable. Water has all these awesome hydrogen bonds and dipole moments. They're too cool to waste their time with a molecule that only has dispersion forces. Water just ignores them and pushes them away. The nonpolar molecules, they aren't really hydrophobic. They're actually just hydroshunned. Anyway, the nonpolar regions of these molecules are driven out of the water and into the center of a spherical structure called a micelle. The nonpolar tails interact with each other on the inside, and the polar heads interact with the water on the outside. That keeps the entire micelle dissolved into the water. Any grease or oily material on your hands, it gets trapped in the nonpolar interior of the suspended micelles, and then they can be washed away. You now have all the concepts you need to be that person who can explain to random strangers washing their hands how soap works. Trust me, this is a great icebreaker in all public restrooms. So, how do you know if a solid will dissolve in a liquid, or if two liquids are miscible? Look at the structures of both of those compounds. Determine the most important intermolecular force in both of those compounds. And if the two intermolecular forces are comparable, the two materials will probably mix. If they aren't, they probably won't. In other words, polar or ionic substances will only dissolve in polar solvents, while nonpolar substances will dissolve in nonpolar solvents. Today we reviewed intermolecular forces and ranked them in terms of their relative strengths. It's important to remember that these intermolecular forces between molecules are generally much weaker than the chemical bonds within the molecules. We showed how you could compare the most significant intermolecular force in a given substance to determine whether a solid will dissolve in a liquid or whether two liquids are miscible. Finally, we looked at the structure of soap molecules and saw how the intermolecular forces in those particles can explain how normally insoluble oil molecules can be rendered soluble in water. In your next class, you'll have the opportunity to apply these concepts again to some new topics.